In this video, we'll be studying about the strengthening mechanisms in solids. So first of all, the dislocation and plastic deformation. So we all know that plastic deformation is correspondent to the motion of large number of dislocations, and in the crystalline solid, we know that the plastic deformation most often involves in the motion of dislocation, that is the linear crystalline defects, the dislocation. So directly speaking, the plastic deformation would depend on the number of dislocation, or we can say that the degree of dislocations. In this figure you can see that there is a process. The dislocations are moving in a specific plane that is called a slip plane. Okay, so here is written that the process by which the plastic deformation is produced by dislocation motion is termed as slip. The crystallographic plane along which the dislocation line transverse is the slip plane. So basically, this plane in which the dislocation is moving due to plastic deformation is called the slip plane, and the dislocation are basically the dislocation motion is called as slip. So the number of dislocation density as discussed previously, or we can say that the dislocation density in a material is expressed as the total dislocation length per unit volume, or equivalently the number of dislocations that intersect a unit area of random section. So the total number of dislocations present in a volume of a material is termed as the dislocation density. Here you can see that the slip lines on the surface of a polycrystalline specimen of copper. You can see these lines. These lines are the dislocation lines, and which are moving in specific directions along with its grain. And here you can see that the alteration of the grain structure of a polycrystalline metal, which is as a result of plastic deformation. Here is the before deformation figure, which has equix grains. You can see that the grains are of a specific dimension and shape, but however, when the grains are deformed during plastic deformation, we can see that these grains are elongated and somewhat stretched. So these grains would be stretched along the slip plane uh, in which the dislocation has been moved. Okay, so the motion of edge dislocation. So dislocation motion requires the successive bumping slip of a half plane of atom. Bonds across the slipping planes are broken and remade in succession. The plastic or permanent deformation of most crystalline materials is by dislocation movement. Most contain some dislocations that were introduced during solidification, plastic deformation, and rapid cooling, that are thermal stresses. To deform plastically means to slide atomic planes past each other. So basically, here is a material. You can see that these are the atoms arranged uh, in a particular form. Here is the line, and the stress is being applied in this direction. So you can see that these atomic lines are moving. This is along the dislocation line, and you can see that these atoms are the bonds are being broken and being remade. So this when this bond will be moving towards this, it would make this bond, and in successive it would be remade and broken. Okay, so how is these dislocations being introduced in the material? So it is introduced basically when the material is solidified from a liquid state, and also while if we suddenly cool or a liquid metal into a solid form, so it causes thermal stresses as mentioned over here. That is rapid cooling. We call it quenching. And it is also caused due to the plastic deformation when a material is being deformed at room temperature. So this is how the dislocations are introduced in the material. Then we have slip systems. So dislocations do not move with the same degree of ease on all crystallographic planes of atoms and in all crystallographic directions. For the movement of dislocation, there are preferred planes. On those preferred planes only, there are specific crystallographic directions. So closed packed plane and closed packed directions are preferable. This combination of slip plane and the slip direction is termed as a slip system. So there are specific directions and specific crystallographic planes in which the dislocation would be move will be moving. So uh, uh, also the closed packed planes are and the directions are preferable for this case. So the combination of this slip plane and the slip directions is termed as a slip system. Here we can see that the slip system of FCC, BCC, and HCP metals. You can see that copper, aluminum, nickel, gold, and silver are FCC with this 111 plane and 1 minus 0. It would in total it has 12 slip systems, while in BCC we have alpha iron, tungsten, molybdenum, and alpha iron again with tungsten, alpha iron with potassium, and it has these 110, 211, and 321 slip planes with their directions, which has all the same directions minus 111, and it has a lot of slip planes, that is 12, 12, and 24. So minimum slip planes are basically 12 for HCC and BCC, while in some special cases like 321 and minus 11, it has the total number of slip planes in BCC are 24, which is only in alpha iron and potassium. Then in HCP, we see that cadmium, zinc, magnesium, titanium, beryllium, and we have zirconium as well. So these are the slip planes and these directions are all same. So it has a slightly less number of slip systems. That is 3, 3, and 6. So the possible slip systems for each BCC and HCP crystal structure are on more than one family of planes. So you can see that in BCC and in FCC there are three families of slip systems. For metals having these two crystal structures, some slip systems are operable only at elevated temperature. We can see that some of these slip systems would only work on high temperatures, not on the room temperatures. Metals with FCC or BCC crystal structures have a relatively large number of slip systems, at least 12, and these are quite ductile as well. And you can see that we have 12 systems for these two and 12 for this family, and these are also very ductile because it can be extensively stretched, and it can also bear an extensive class of deformation, like you can see in copper, iron, and aluminum. On the other hand, HCP metals have a very few active slip systems and are not quite ductile but are usually brittle. Okay, so let's move forward. Dislocations and mechanical properties. The strength of a material with no dislocations, or a material which has a very unique crystal structure or is a single crystal is 20 to 100 times greater than that of the strength of a material with a higher dislocation density. But in reality, a material with no dislocation does not exist, and if it exists, if you try to make it, it's very difficult, and we cannot do it commercially. So uh, the dislocations weaken as a material but make plastic deformation possible. So we know that the dislocations, while the dislocation uh, moves around a specific slip plane in a slip system, the material is strength is being compromised. But on the other hand, we can uh, conduct plaster deformation. We can cold work our material. We can change the shape of the material if we want. For example, if we have a metallic sheet and we have to bend it, so we'll be hammering it on a certain direction to in order to bend it. So in order that the sheet should be bent, uh, the sheet must bear plastic deformation. If the sheet would not bear plastic deformation, or so it would not bend, then it would break easily. So basically, dislocations help the material to deform plastically. So the mechanism of strengths in metals are three. There are strengthening mechanisms, that is grain size reduction, solid solution strengthening, and strain hardening. So we'll be discussing these two in this lecture, and the third one in the other video, in the next video. So dislocations and mechanical properties. We've done this. Okay. So grain size reduction. Grain boundaries are barriers to slip. Basically, you can see that we saw grain boundaries in this video. In this slide, we can see that this is the grain boundary. Okay. This is a coarse grain, and you can see this grain and this grain. So these basically these are the grain boundaries that separate two different grains. Okay. So grain boundaries are barriers to slip. Barriers strengthen or increases the angle of misorientation. The smaller grain size, more barriers to slip. It is based on the fact that dislocations will experience hindrance while trying to move from a grain into the next because of abrupt change in orientation of planes. Here you can see that this is a slip plane and the dislocation would be moving in this direction. But on the other hand, we have also studied that the higher angle grain boundaries and the lower angle grain boundaries. This is basically a higher angle grain boundary. So this is also another grain which would resist this dislocation movement. So while we'll be applying the load, the stresses will be generated inside this uh, in these atoms, and the atoms would be moving, and the dislocation would be moving along this plane, and the dislocation will also be moving along this plane. So this is the grain boundary. So along the grain boundary, the this provides a barrier in order to further proceed the dislocation movement, and that would cause the uh, strengthening to be introduced in the material. So since on a higher load, on a higher stress, the material must move, but since the misorientations are very high, so in that case, the, there would be a barrier, and from that barrier, basically, it would hinder the dislocation movement, and ultimately, the material would resist the high load, and therefore, the material would have a higher strength. So by this, the strengthening is increased. So misorientations are very desirable in order to increase the strength, and lower grain sizes, and fine grain size, we call it a small grain size, we call it as fine grain size, is desirable in order to increase the strength. But in this case, the ductility is being compromised because the plastic deformation is being resisted at the grain boundary. So the other method is grain size reduction techniques. So if we want to reduce the grain sizes, what we'll choose is we'll choose the solidification pattern according to that. So we'll be increasing the rate of solidification from the liquid phase. Uh, what I mean to say is, if we are casting from the liquid state to a solid state, uh, so we'll be directly reducing the temperature to a very lower one, uh, as the since the rate of solidification would be increased, so the small grains or the fine grains would be produced. Perform plastic deformation followed by an appropriate heat treatment. Okay, so the grain size reduction also improve toughness of many alloys. Small angle grain boundaries are not effective in interfering with the slip process because of the small crystallographic misalignment across the boundary. Boundaries between two different phases are also hindrance to the movement of crystallizations. This is what I discussed in the previous slide. So here you can see that this is a 10 micrometer graph, a micro structure. So you can see here that these are the small grains and these are the coarser grains, or the some, what we can say, a high dimension grain. We call it a coarse grain. Okay, so in a higher size grain, you can see that the misalignments are not very effective, or in a lower angle grain boundary, the misalignments are not very effective. They are effective, but somewhat it is lesser than that of the small high angle grain boundaries and small size, that is the fine grains. Okay. Next we have is solid solution strengthening. Before that, I'll be just reiterating what I said is, if we reduce the grain size, the hindrance between dislocation movement is increased, and therefore the plastic deformation would be resisted. And if the plastic deformation is resisted, the strength of the material is increased. Okay, because we are applying the load, but there is no plastic deformation being held. Okay. So that means that the material's strength is very high. Okay, so let's come to solid solution strengthening. So impurities atoms distort the lattice and generate stress. Stress can produce a barrier to dislocation motion. Impure foreign atoms in a single phase material produces lattice strains which can anchor the dislocations. Effectiveness of this strengthening depends on two factors: the size difference and volume fraction of solid. Elastic modulus and long range order interactions are of long range, that is, they are relatively insensitive to temperatures and continue to act about zero point 0.6 Tm is the melting temperature. Okay, so we'll be discussing all these points in the later slides. So small impurities tends to concentrate at dislocations on the compressive side stress, right? Reduce mobility of dislocation increases. So the same thing is being happening, that is, we are providing a hindrance to the dislocation motion, but in this case not with the grain size, but uh, we'll be discussing this in when an impurity is added, or interstitial impurity is added inside our material. You can see that this is a foreign atom, this is an impurity atom. So how it is desirable that the size is smaller, uh, atom size is smaller than that of the lattice. So you can see when the size is smaller, and if this is introduced in the slip system, the dislocation line, you can see that it provides a compressive strength. These atoms will be applying stress to uh, these foreign atoms, and when the stress would be applied, uh, you can see that these atoms would cause hindrance again in the dislocation movement. All right. So in that case, the uh, again the dislocation is being the dislocation movement is being compromised, so the strength would be increased, and again the plastic deformation would be resisted over here. And in case of a large impurity atom, at dislocation on the tensile side, pinning dislocation. Okay. So in this case, when the size of the impurity atom is larger than that of the lattice, the parent lattice, So the stresses would be generated. The stresses generated inside would be tensile. Again, this would cause the hindrance uh, in the dislocation movement, the line of dislocation, and the dislocation movement would be resisted by that hindrance, and again, plastic deformation would be compromised, and the strength would be higher, would be increased. So you can see over here that as this is a copper uh, alloy, and in which we are adding nickel. So we can see that as the percentage of nickel is being increased, here nickel is the solid, the impurity, the foreign atom which we are adding in the copper solution. So when we are adding, when the percentage of nickel is being high, you can see that the tensile strength is being increased. Why? Because these the atom of nickel provide hindrance in the dislocation movement of copper atoms. Okay, and also this you can see that the yield strength is being increased as the percentage of copper, as the percentage of nickel is being increased. Okay, so this was all. We'll be continuing this lecture in the other video, and we'll be discussing strain hardening in that. So thank you.